Yes, okay, thank you very much. So good morning. So where did we stop yesterday? So yesterday we said that whenever you have even lattice L, then attached to this guy there is a vertex operator algebra, a bosonic vertex operator algebra VL. And if the lattice is self-dual, then this algebra has only one representation, and it can just stand by itself and be in the whole conformal field theory. So in this case, this is essentially the same as the space of states of our conformal field theory. So our conformal field theories only have holomorphic fields in this case. Okay. If this is not self-dual, you can still define the vertex operator algebra, and you can use it as a chiral algebra in that case, but then it will not be, I mean, the whole CFT, but there will be other fields and will be not be holomorphic in general, okay? Also, actually, you can take L not to be even, but just to be integral, so that all scalar products are integral, but not even norms. And then in this case, you get fermionic VOAs, so VOAs with fermions in that case. That's what changes, okay? So in particular, we went up to central charge 24, so dimension 24. One can go on if we want. So a central charge of 32, there are a huge number of even self-dual lattices, and the number explodes afterwards. So you have a lot of these guys. But a central charge 24, we have 24 Niemeyer lattices, so we have 24 of these theories here. And the partition function of each of these theories, well, it must be modular invariant, and essentially by modular invariance, it's constrained to be the J function plus some constant, and the constant is the number of currents in the VOA, which is essentially 24 plus the number of elements of vectors of length 2 in this lattice, essentially. Okay. So there are two problems here if we want to explain monstrous moonshine. So the first one, as I said yesterday, we have no such theory where this is 0. Okay. The second is that, well, okay, this is just the SL to Z invariant function, but monstrous moonshine concerns a lot of Haupt modules with many different groups. So where do these other functions come from? So as I said yesterday, this come, or in the first lecture, this should come from symmetries of our VOA. So all these guys have some nice group of symmetries. So let me be fancy, called automorphisms of the VOA algebra. So these are symmetries that commute with Virasoro, okay? Because I don't want them to mess up with conformal transformation. So let's say they commute with Virasoro. And for example, if you take the Leech lattice, okay, then you know for sure that this contains at least U1 to the 24 Lie group, which is generated by the 24 currents. Okay, but actually it's a bit bigger than that. So this is a normal subgroup here inside, and if you quotient this out, you get a nice finite group, okay, which is known as the Conway group, Co-naught. Okay, and this is the group of automorphisms of the Leech lattice that you start with. So essentially this U1 to the 24, what they do is they act on all these states by phases. Okay, this is what the U1 to the 24 does. But this Co-naught, what it does, it exchanges one vector to another. Okay, and it goes on like this with essentially there's something similar for each of these lattices. So there is always a Lie algebra group of symmetries, which is generated by the currents. That's a normal subgroup. It's called the inner group because it's generated by the zero modes. But then you have an outer group usually, which is related to the group of automorphisms of the lattice you start with. So just to give you another example, for example, there is a Niemeyer lattice, which with the A1 to the 24 root lattice. So this is not just a root lattice. There are many other vectors that you need to generate a full Niemeyer lattice. And then, so this contains a SU2 to the 24, okay, inner group. And then if you quotient it out, SU2 to the 24. And if you quotient it out, you get a nice finite group, which is essentially related to the group of automorphisms of this lattice here, which is called Mathieu group M24. Okay, it's a subgroup or a permutation group of 24 objects, and it just permutes the 24 SU2s in some nice ways. It has to permute in some nice ways so that it preserves the vectors that you added to this root lattice, okay? It doesn't maps you out of the lattice. So we have all these groups. None of them is the monster. We don't get close. Actually, we have all these continuous things. So now, what can we do with these groups? So let me be more general now. Suppose you have a CFT H, which is not necessarily holomorphic, okay, any CFT. And suppose you have a group of symmetries, let's call it G, okay, that commutes with Virasoro. And let me take it finite, because then it's easier, otherwise it's a mess. Okay, so if you want, it can be a subgroup, a finite subgroup here inside, okay? Now, there's an obvious thing that you can do with your partition function, and we did it already, okay? So Z of tau, the partition function as it is a trace over H of Q to the L0 minus C over 24, Q bar, L0 bar minus C bar to the 24. And then what you can do is you can pick up any element, call it H, in this finite group, and you can put it inside a trace, okay? So we call it ZH, this guy. Okay, very good. This commutes with Virasoro. So essentially it acts on any, so any Virasoro eigenspace is a representation, okay, of the group G, okay? Now, what kind of modular properties does this thing have? Well, so how do you find this thing? So essentially, if you have your torus here, okay, so what happens is the following. You start with your state here. The state propagates in Euclidean time, but then before closing the loop, what happens is that you insert this H here. So it acts on the state. There's something that acts on the state with this H before closing the loop, okay? So a nice way to see this, to describe this, is saying that you're taking a partition function on a torus with a defect inserted here. So the defect, what the defect, this line defect does, it creates some sort of singularities of your field. So when the fields cross the defect, they're not continuous, but they just transform under H. So it is a topological defect, means that you can move it, okay, deform it continuously. So it doesn't matter where you put it. Important is that there is this defect when you do the loop, okay? So from a path integral point of view, what you're doing, so if you want a path integral description of what you're doing, so if we had a partition function, you would say that the fields must be doubly periodic, and this is the condition that you put on to have the theorem of torus. But now what we want to do to have this H here is to be periodic under the A cycle, but to be periodic only after this H action under the B cycle. So as I go around the B cycle, I want this kind of condition. So I want H to act on my fields as I go around the B cycle, okay? Now there's an obvious generalization of this thing. So since I have some condition when I go around the B cycle, I can maybe put some other condition, let's call it G, as I go around the A cycle. So that will mean that I have another defect, but wrapping the other way, okay, in the other side, so that as I go around the A cycle, I cross the defect, and then I get transform my G, and as I go around the H side, I cross this. So this I call ZGH, okay? Now the question is, what is it in the operatorial formalism, this thing? Well, what happens here is that actually I'm inserting this defect here is really actually changing my theory in a sense. So I'm not considering anymore the space of states of my CFT on a circle, which means that everything is periodic on a circle, but I want to consider a space of states which are not quite periodic on a circle. So I'm kind of modifying my theory somehow. There's something that modifies my theory. So I don't have the same space of states that I had earlier, but I have a new space of states which I call HG, okay? So this HG is the space of states on a circle, but with some singularity inserted on a singular essential. Okay, so this is called the G twisted sector. So it corresponds. So in the cylinder, you're just inserting this guy here, maybe like this. Okay, some way, and if you do state operator correspondence to the C minus the origin. So what this corresponds, it corresponds to an operator at the origin, but not a local operator. I mean, some operator that is attached to a defect. Okay, this is what happens. So the state operator correspondence tells me that these states here are in one-to-one correspondence with operators that start the defects. Okay, like this. And this is not a local operator because it has some no locality here. So when I try to act with some other operators in my CFT here, if I move the other operators around, the thing is not quite periodic, but they have this discontinuity. Okay, so I have some non-locality. Okay, so these are most general things that I can get. Every time that I have a group, I can take these things. So what are the modular properties now? So as was described many times, so modular properties means tau goes to A tau plus B over C tau plus D. So this is just, so it's essentially a conformal transformation of your coordinate, Z over C tau plus D. But then what you're also doing is you are changing the basis of cycles in your torus, okay? And Ollie gave the transformation for the basis of cycles. So if you start with a B cycle and A cycle, this gets transformed into B twiddle, A twiddle, which is given to AB plus BA, CB plus DA. Okay, so these are the new cycles that you get under this modular transformation. So this is just if you want a change of basis, not much. But this tells you something about how this guy transforms, because so this should be, morally, this should be invariant, okay, under modular transformations, okay, except that now, so this is what happens when you go around the A cycle, this is what happens when you go around the B cycle. So what you have to put here is, you have to put what happens when you go around A twiddle and B twiddle. Okay. So what happens when I go around B twiddle, for example? Well, B twiddle means I go around A times around B and B times around A, okay? And what I get is something like, okay, so let's do it right. So around A, I get the G. Exactly, yeah. So around A, I get A. Okay, around B, I get H. So it should be HAJB, if I'm not mistaken. And then the same should be HCGD. So one thing that I forgot to mention, okay, so H to the C, G to the D. I hope this is visible. H, A, G, B. Okay. So one thing that I forgot to mention, what if G and H don't commute? Well, if G and H don't commute, these periodicity conditions don't make much sense, actually, because now, if you ask what happens if I go around both cycles, well, you should be able to do this going around the A cycle and then the B cycle, or vice versa. Okay, so this should be around equal both to GH phi of Z, but it's also be equal to HG phi of Z. So for this, in order for this to make sense, or better, to get something which is non-zero, okay, if you want, then these two guys better commute. Okay, so this thing is well defined, or if you want, you can say that it is zero if you do something bad, because you don't have any fields that satisfy these conditions, essentially. So these guys should commute. Okay, and then if these guys commute, then you don't care how you order them. Okay, so what you see is that If you take the set of all these ZGH, as where G and H are commuting pairs, okay, of elements in your group, essentially modular transformations just move them around. Okay, so they form, if you want, they form a vector valid modular form under cell to Z. Okay, or modular function actually. So all Z, G, H, where G and H are in G, and that commute are, these are the components, all components of a vector valid modular function. Now, vector valid modular functions. So, okay, one more comment. Actually, in general, you have to allow for possible multipliers here. Okay. Now, these multipliers, so this should be true, but in general, it is only true up to phases. Okay. Now, so this multiplier here is not very much related to the different central charges as it was before. It's quite unrelated to that. It's a different anomaly. Okay, this is a 't Hooft anomaly for the group G. Okay, that's one interpretation of the thing. And if you want, the problem there is the following. So this is related to 't Hooft anomaly for G, for your global group G. And essentially, another way to see this is to see what happens when you have a network of defects. Okay, like you have a G defect, an H defect, they can merge into a GH defect, and then they can join a K defect, like that. Okay, but then as you move these guys around, you can change this configuration to a different network of defects. For example, this one. Okay, if you move them continuously. So this is GHK, and this is, again, the product of the three. Okay, but they are joined in a different order. So if you think that if they are topological, you should be able to move them around, but actually when you cross this guy, it happens that this thing is not necessarily identical. When you insert something like that in a correlation function, and you do this kind of move, you don't necessarily get the same correlation function, but you get the same correlation function up to a possible phase. So there's some ambiguity in how you define this phase, because roughly speaking, you can insert some operators here at the junctions that what they do, they just change a little phase every time that you have a GH junction. You change a phase in a given way. Every time you have some other junction, you change the phase in some other way. So this changes this alpha GHK. And also this alpha GHK must satisfy some constraints, which are given by what happens. So this, you can see this as a, if you want, a problem with associativity of defect operators, in the sense that if you have three defect operators that start a defect, if you join first the first two and then the third is different from joining in the other way. So that's a problem with associativity of the OP, if you want, okay? And there is a constraint which comes from what happens from associativity of four of these guys. So that's a pentagonal identity, if you ever seen this, but that's it. So all these things tell you that what matters is not exactly this guy, but this guy is very constrained and it has some ambiguity. So what happens is that this guy defines some class in some kind of cohomology that I'm not going to define, but that's defined in that way. Okay. And every CFT that has a group G, okay, has some associated 't Hooft anomaly that takes values in some cohomology, and the cohomology depends on the group G. So which class it is, that depends on which CFT you're looking at. So different CFTs with the same group might have a different anomalies, as it usually happens, and this is the, okay. So yet another interpretation, then I stop. This you can also see as passing from here to here. You can also see it as saying, I do a local symmetry transformation in this region here. I multiply everything that is here by the symmetry H, or H minus 1 maybe, okay? If I multiply everything with the symmetry H, then this defect becomes trivial, and then somehow I have some other defect appears here. So this is like a local transformation, okay, in this region here, okay, by the symmetry H. And the fact that you get a phase means that when you get a non-trivial background somehow for your finite group and you do a local transformation in some region, then you get some weird phase, which is kind of the definition of a 't Hooft anomaly. So that's why it is a 't Hooft anomaly. Okay. So these guys enter in the modular transformations because when you are on a torus and you have the two defects that intersect, you can actually see them in different ways. So you can see them as something like this, okay? Or you can see them as something like this, okay? Okay, so one is G, one is H, they fuse, and then they split again, or they can fuse in a different way. So these two things are related by this kind of moves. And when you do modular transformation, so you can decide, okay, my ZGH is given by this kind of networks always. But then when you do the modular transformations, then you might get something like that, and then you have to come back. And when you come back, you get the phase. Okay, but then so these guys, this is to say these phases are not random at all. Once you know this anomaly, you know the phases. Okay, very good. Now you have a vector valued. We have a vector valued modular form. So vector valued modular forms, we found them as characters in some chiral algebra. Okay, and we kind of wonder, okay, are they characters in some chiral algebra? And the answer is yes. So now, so everything that I said so far was true for general CFTs, not necessarily holomorphic. But now let me turn holomorphic. Okay, so let's go to H is equal to a VOA, holomorphic VOA with only one representation. Okay, as the ones that is shown. So in this case, these ZGH are, so only in this case the ZGH are holomorphic. Of course, in the other case, they were not holomorphic. They have nice these modular properties, but were not holomorphic. But in this case, they are holomorphic guys. So in this case, you do expect them to be characters of some algebra. So which algebra is this? So let me do in the stupid case. So let's say that our group G is just a cyclic group, so something like Zn generated by this element G, okay? Now in this case, you can do something stupid to your algebra. You can decompose it into eigenspaces of G, okay? So you decompose it into eigenspaces of G, so let's say this is the should I call it K here? Let's keep the same notation. Let's call it S. Okay. So this is the eigenspace where G is this root of unity. So yeah, and then this is a sum from 0 to 1 minus 1 of the eigenspaces. So in particular, you have when G is the identity, you have something which is the G invariant subspace. So I denote in this way. And only for the identity, this is actually a subalgebra, okay? Because in this case, somehow the commutation relations just keep you inside the invariant part. While in the other cases, the other spaces, yeah, you don't stay, taking commutations, you don't stay inside each of these spaces. So you have a subalgebra which is a subalgebra of fields which are invariant under G. And then these guys are representations of this algebra because when you act with the invariant fields, you stay inside one eigenspace. So these are reps of VG, okay, of this subalgebra. So this is not holomorphic. This is not holomorphic. It has many representations, so that's fine. And so what are the characters of this guy? Well, what you do, you take a trace over V, and you just insert a projector on the eigenspace that you want. Okay. So for example, for the S, for a given S, what you do for the character, so the character associated with the S eigenspace, okay, is given by the trace. You take a trace over V of the usual stuff, Okay, it's solomorphic, so it does only this thing. And then a projector, the way it looks, it's you take just 1 over n. Well, let's do the invariance. The invariant thing is 1 over n sum over k gk. So this is a projector on the invariant part. Okay, 1 over n sum of gk is the projector on the invariant part. And if you want the s part, you just insert e to the minus 2 pi I sk. E to the minus 2 pi I sk over n. So this is the projector on the s piece. Okay. But then you see that this guy here is just your z nothing on the A cycle and g to the k on the B cycle. Okay? So you see that the characters, so these are not quite characters of a thing, but you slightly change the basis and then you get the characters of the representations of Vg. Okay? But then you see another thing, that if you take just these characters or these representations here, okay, you don't get all components of your vector valued modular form, because if you do modular transformations of these guys, then you start to see also the twisted sector guys. So these are not enough. So these are not all representations of Vg. So this tells you is that Vg has also representations from the twisted sector. Now, what's going on? So what are these twisted sectors? Okay. So let's say you have the G to the R twisted sector now. Okay. Now, is this a representation of V? Is this a representation of Vg? What is it? So the answer is, this is not a good representation of V. Okay. And the reason that it's not is exactly that in a good representation of your vertex operator algebra, if this is the space of states on a circle, you want to be able to insert any operators in your algebra to act with any operators, and then when you move them around the circle, you want to have periodicity. This is a good ordinary representation of your algebra. And this is not a representation of the algebra. So the fact that this has only one honest representation, it's safe, because this is not an honest representation, and that's what is called actually a twisted representation. But what happens with Vg? Well, with Vg things are better, because Vg is done also only of fields that are invariant under G. So when you move them around the circle, even if you have the defect, you don't see the defect, okay? Because they are invariant. So they are periodic as you move them around. So this is an honest representation of your G invariant algebra. So if it is an honest representation, then you have to include these guys in the list of your representations and in your vector valued modular form of your representations. So what you can do is to make the same decomposition into eigenspaces, because of course also this guy decomposes into eigenspaces of G, and every eigenspace is actually an irreducible representation. This is not irreducible as a representation of Vg, okay? But it becomes irreducible when you decompose it into the eigenspaces. And when you decompose it into the eigenspaces, what are the characters? Well, the Rs character, which is the character on GR with eigenvalue e to the 2 pi I s over n, is just the same thing, but with the VGR here. Okay. So the character, so you have this Rs character. So you have two indices, one that tells you that you are in the twisted sector, and this tells you the eigenvalue of G on that twisted sector. And they are, you see that you are using essentially all ZGR GK, and then this tells you that these are indeed this vector valued modular function corresponds to the characters of this algebra, okay? But you have to change a little bit the basis, okay? You have to do this kind of discrete Fourier transforms and stuff to get the real thing, okay? So this works for a cyclic group, works much more generally, actually. So if you have a general non-abelian group, what you get is that you get the twisted sectors are labeled by conjugacy classes, So different twisted sectors are labeled by conjugacy classes because if 2G in the same conjugacy classes give rise to twisted sectors which are isomorphic, okay? And then on each twisted sector, you don't have a representation of the full group G, actually, but you only have a representations of the elements of G that commute, the elements of the group that commutes with the twist, if you want. Okay, that's a condition that you can take, you know, when you have a G, then you can take only the H that commute. So in general, the representation of the invariant algebra are labeled by a conjugacy class and by a representation of what is called a centralizer, which is nothing but all the subgroup of elements that commute with G. Okay, and actually, if you want to be very, very careful, this is not necessarily a honest representation of the centralizer. It's a projective representation of the centralizer, projecting in which way? Well, the anomaly tells you, okay, how to do things. Okay, so there's a projectivity here, but it's determined also by the anomaly. So that's a general story with the orbifolds. And you can generalize this story to defects that are not symmetries. Okay? You can do the same thing with also with other kind of defects, but okay. So all of this to go where? Well, we go to this thing now. You can create an orbifold, okay? So what is an orbifold? Well, essentially, as this thing, instead of taking, so your original vertex operator algebra was given by a bunch of representations of Vg, okay? With all possible eigenvalues of G and no twist, okay? But you can do something different, okay? You can take some other thing, okay, that is given somehow the other way around, which means that you take all possible twisted sectors, okay, but then you take only the invariant part in each twisted sector, okay, so only the trivial representation in each twisted sector. And then if you look at the partition function or the character of this thing, what happens is that, well, you have to sum over the characters or r, comma, well, maybe 0, I should say, okay? So you get a 1 over n, a sum over r, a sum over k, and then this guy is trivial, okay? And then you get z, g to the r, g to the k, okay? So this is the character of this representation here. And you see, if you don't have anomalies, okay, so if you don't have strange phases, what happens is that this thing is modular invariant, okay, because modular transformation just permute this thing into one each other, and then if you sum over all of them, then, yeah, it's modular invariant. So this has a good chances of being a holomorphic VOA, and actually it is a holomorphic VOA if you have no anomalies, because if you have anomalies, then this is not modular invariant and things break down. And as you expect, because this is a kind of discrete gauging of your global group, and you know that Toft anomalies are obstructions to gauging, essentially. So that's the general story. And you might be worried because you said, okay, but these guys have non-local operators inside. Okay, so I want to have local operators in my theory. But actually, you don't see the non-locality, okay? Because the non-locality is seen only by operators that transform non-trivially under G. But here I have everything which is invariant under G, so all these defects that these guys create, there is nothing that can see them, the defects, so they become local. Okay, so when you restrict the things, they are mutually local, that's the point. Okay, so this is an honest VOA, so this is, okay, and this construction you can generalize to other kind of defects, okay, that are not given by symmetries. And this is some kind, what is known as a generalized orbifold, and you can do it if you don't have if somehow the defects join in a nice way, which is the analog of not having anomalies. Then you get something consistent. And actually what happens, so you can do it in holomorphic VOAs, you can do it in non-holomorphic CFTs. And what happens actually is that if you have a rational CFTs, okay, you can have rational CFTs with the two different rational CFTs with the same chiral algebra, okay, because maybe you are putting in different representations, okay, and two different CFTs with the same chiral algebras are always related by a generalized orbifold of this kind, where the defects preserve the chiral algebra. So you can always go to one theory to another doing this kind of procedure. So it's in a sense very general if you take general defects. Okay. So, and now we get to the monstrous Moonshine finally. Yeah, okay, and then I stop. So, what we do, we want to eliminate these stupid currents, okay? But we can eliminate the stupid currents, okay? We just have to take any of the other lattice VOAs and then do the orbifold by some symmetry under which the currents are not invariant. If the currents are not invariant, they are thrown out of the orbifold. Okay, they're projected out, so in my new VOA there will be no currents, hoping that there are no new currents coming from the twisted sector that I added. So the easiest way is to start from the VOA that has less currents, which is the Leach lattice. And that's actually the only way if you want to do cyclic orbifolds to get the natural. So you start from the Leach lattice, so you have the 24, you have just the 24 U1 currents that you started with, okay? And I want some symmetry of this guy that gets rid of these currents, and there's a very, so you have many choices actually. A very stupid choice is a symmetry that's somehow charge conjugation of U1, so you, and then you also have to map every vector to its opposite vector. So, okay. So this is a Z2 symmetry. Okay, so things that survive are things like these survive, are invariant, and with the minus sign they're not invariant and projected out. So you do the orbifold in this way. It's a Z2 orbifold, so you get just one twisted sector. You add a twisted sector, you get a new VOA that you might want to call V natural at this point, and you have to check that from the twisted sector you don't get currents, okay, from the twisted sector, but this you can compute the character of the twisted sector doing modular transformations of the characters that you have, and you go there and check, okay, do I have operators of conformal weight 1? The answer is no. Okay, they are higher conformal weight that enter from the twisted sector. And then you are done. You have a theory that has no currents. Now, it's a modular holomorphic theory, central charge 24. Necessarily, the partition function of this theory is the J function without any constant added. And more than this is true, so Frankel, Posky, and Moerman proved that this theory here has a symmetry group. That now it becomes finite, the symmetry group. You don't have currents, so you don't have the continuous part, and you just left with a finite symmetry group, but it's a big one. It's the monster group. That's what they proved. So this is the guy. Okay. So we obtain it with the Z2 orbifold of the Leach lattice. There are many other orbifolds of the Leach lattice by cyclic groups. You have to act non-trivially on all currents, and you always get, when you're able to get rid of all currents, you always get the natural, the same thing. Okay, you don't get different guys. Okay. Actually, the different ways to get the orbifold help you in understanding that the symmetry group is the monster group. Because somehow, every time that you do a orbifold, you somehow inherit some symmetries from your original theory, the ones that commute with this. Essentially, this you inherit. But then, these has more symmetries that you don't see from the orbifold construction. But if you have many orbifold constructions to the same theory, then you can put together everything and you get the monster. Okay. And now, if you get the monster, then you can build all these guys for the monster, and you know that these have nice modular properties. Okay? So in particular, actually you get even more than what you expected. Okay? You expected just a single element here. So what people found were only the untwisted cases, which were the easy, the clear ones to find. Okay, so this how module TG, okay, that are in the monstrous Moonshine conjecture. Did I? Yeah. Okay, let me call them TH now. These were the functions that were in the monstrous Moonshine conjecture. Now they should be these functions here. Okay, and in the monstrous Moonshine conjecture, we're not saying, oh, it's a vector value, the modular function. We're saying they are invariant under some subgroup of SL2R. Okay, and if you check the invariance, essentially what you get is that, okay, suppose that this has order n, okay, and if, yeah. No, you have to add also these other guys. Yeah, by themselves, no. So these are some components, some of the components. Yeah, they are invariant under some smaller group. Okay, and this you know from CFT essentially. And if you look at the modular transformation of this guy, which I erased, but it should be probably something like that. Okay, when this is 1, this is something like this. Okay, then okay, this should be equal to this. I think it was a formula like that. Why can't I find it? Oh, okay. Yes, I was right. Okay, up to a phase possibly. Okay, and then if you see that if C is 0 mod n, and if A is 1 mod n, then this is invariant. Okay, because here you have 1, and here you have h to the 1 essentially. Okay. So if you have these two conditions, then you automatically have also that D is 1 mod n from the determinant being 1. Okay, and this gives you gamma 1n. Now, sometimes things are better than this, because sometimes h to the a, if a is coprime to n, sometimes h to the a is in the same conjugacy class as h, actually almost always, okay? It's in the same conjugacy class, so you don't really care about this condition here, okay? Essentially, for the monster group, essentially, this condition you can drop, and then the group that you get is gamma 0n, where you only have this condition here. Possibly up to phases, okay? Little problem, from CFT, so you get all these functions, they are modular invariant, and CFT justifies why they are modular invariant. The only thing is the groups that appear in monstrous Moonshine were not always subgroups of SL2Z, they were subgroups of SL2R. Sometimes there were some other element outside SL2Z, okay? And these were important because only if you add these other elements, you always get a genus 0 group, okay? If you just stick to these guys, these sometimes are genus 0, but not always, okay? And in general, this is not the how module if you skip some guy. Even if it is genus 0, it's not necessarily the how module, okay? So this other property, you do not explain with CFT. Okay, there's no way to explain this with CFT. So this CFT construction works for every CFT with any group of symmetries. You can do this thing, and you get modular functions. This is extremely general. The genus 0 property is a property of the monsters of this particular CFT, and you don't explain this way. There's a way to explain this, kind of, using bosonic strings, or maybe heterotic strings, okay? But I don't think I will get there tomorrow, but I will say something about that. And at the end of the day, let's say, this is deeply related to the fact that the monster CFT has no currents, So, okay, general story about CFTs and central charge 24. They're not only the 24 that we said, yes, because we have all the orbifolds now that you can build. And actually, it turns out that taking orbifolds, you get a full list of your conformal field theories of central charge 24. So more is true. Taking orbifolds of the Leech lattice, of this Leech lattice VOA, you get all the other ones, okay, if you want. The only thing that we don't know is if this one is the only one without currents, okay? This we don't know. But if there is another one, if there is another VOA, a central charge 24, that has no currents, whatever symmetry group it has, one can show, kind of, that these guys will be genus zero as well, using a string theory construction. Okay, so this genus zero property is related to the absence of currents, and just I give you a little bit of flavor just to, okay, when you do bosonic, this has central charge 24, which is nice, it's very close to 26, okay? So you can try to do also bosonic string theory, putting 24 dimension on this CFT, and then the 2 dimensions you put into one space and one time dimension, let's say. Okay. So you do something like that. So you can do this. Now this is holomorphic. So a weird thing that you can do is you try to do chiral string theory, whatever that means. But so you try to take only half of it, okay? You have to do something strange with your space and time dimension to do this. But you can do, but Borges did it formally, okay? So if you do it, then you can look at the physical states of your string theory. There is things like light cone quantization, et cetera, et cetera. So you can do with natural, you can do with CFTs with F currents. But if CFTs have currents, okay, what happens is that the currents corresponds, roughly speaking, to massless physical states in string theory. Okay, so roughly speaking, this is the only theory that has no propagating massless degrees of freedom. Okay, and this is related to the genus zero property somehow. So that's a bit the flavor of what happens. Okay. Okay, so I stop here with the monstrous moonshine. How made one? Should I do a 5 minutes break? I think it's a very good, because then I start with the Mathieu moonshine. Yeah. Yeah.
There is a little bit of a queue for the coffee because there's only one coffee machine working.
Oh, yeah. Più o meno, sì.
Sì, pure 10. Quello ricordo che è sbagliato.
Mm-hmm. Ok, ok. Sì, perché voglio un pochino, se no non riesco. Cioè, se dopo farò un po' meno di quello che pensavo, però voglio finire un po' di roba domani, se no no. Di discussione, sì, vabbè.
sorted the coffee problem, so people could hear coffee.
Okay, good.
I'm hoping that everyone's letting me know that hot coffee machines are now working.
Okay, good. So one very, very last comment. So the original Monsters Moonshine conjecture was about essentially the functions were 1 comma h, but actually you see that they have many more functions in the end, and it turns out that they are all Haupt module of genus 0 groups for different groups. Okay, so they are more, so they are not gamma node n with something else. They cannot be gamma node n because when they have G, yeah, they are a bit different, but they're all genus 0 groups done in a bit different way. Okay, so and this is called generalized moonshine. So this was conjectured by Norton, and then the proof is actually not so long ago, like 5-6 years ago, by Scott Carnan using methods, extended methods by Borges, essentially. So that's it. So so now, so I like the Monsters Moonshine because it's a really exceptional thing. It's like E8. Now, these kind of things that just sporadic pop out like that, and you don't know why on earth they do exist, and they have these monstrous things that just connect to get something that works. Okay, but then you might say, okay, what the heck? I mean, what do we do? Chiral bosonic strings? I mean, what do we use for in string theory? So recently, there have been recently, 15 years ago, new examples of moonshine that actually concern theories that are very, very well studied in string theory and in superstring theory. And in particular, supersymmetric nonlinear sigma models on K3 surfaces. Okay? So this means that you have your worksheet of your, let's say, type 2. Or you can take type 2A or type 2B, doesn't matter too much. Type 2A or type 2B superstring, okay? And then, so this is 10-dimensional, then you take 4 of these 10 dimensions, let's say from x6 to x10, you put in this thing that you might recognize as a K3 surface, and, okay, so a K3 surface is a manifold, so real dimension 4 or complex dimension 2. Okay, that's why it's called surface. And that's the easiest example of Calabi-Yau manifold. So it's a Calabi-Yau twofold. And it's actually the only Calabi-Yau twofold that is closed, so compact manifold, and simply connected manifold. Okay, so Calabi-Yau threefolds, you have who knows how many, okay, different topologies. Calabi-Yau twofolds, you only have this. So that's kind of the simplest example of Calabi-Yau compactification in string theory. That's one step farther than torus compactification. So that's your first step beyond torus compactifications. And it's actually very non-trivial on one side, but much, much simpler than Calabi-Yau threefolds on the other side. So you can actually work and find things with some things with these K3 surfaces. And so compactifying on K3 surfaces like breaks half of your 10-dimensional supersymmetries. So for example, you can put your theory on K3 cross T2 if you want to go down to 4 dimensions, and then you have 16 space-time supersymmetries, essentially, if you do type 2A or type 2B on K3 cross T2. So it's n equals 4 in 4 dimensions. Okay, so these are your theories, and these were very well studied because this was these were the first theories in string theory where people try to compute like microstates of supersymmetric black holes and try to match the number of microstates with the entropy functions that come from Bekenstein-Hawking formula or generalization like Wald formula, etc., and matching them, at least in the limit where your black hole, where your formula are valid. Okay, so for big enough black holes, you can do the calculation, and you can do the matching essentially in these theories. Okay, so these were very important, and so we look at the CFT. Okay, so we look at perturbative type 2 superstring on a K3 manifold. So we ignore the other 6 dimensions, and we just focus on these 4 ones. So it's supersymmetric, so you really have morally the 4. You have also the super partners, so these guys, but these are not like free fermions. They are coordinates on this K3 manifold, okay? So you have a super conformal field theory, okay? So you actually have a lot of super conformal field theories because being a sigma model, the theory that you get depends on a metric and a B field that you put on this K3 surface. So you have a metric and B field to choose, okay? So you don't get just one conformal field theory, you have a whole moduli space of conformal field theories. So if one has a look at how big is the moduli space of metrics and B fields on a K3 surface, you get an 80-dimensional moduli space. Okay. So how much do we know about these conformal field theories? So on one side, we know a lot. On the other side, we know almost nothing. Okay. So what do I mean? So in this 80-dimensional moduli space, there are some special points or some special submanifolds where we really know everything about the CFT. Okay. For example, there are things like orbifolds of T4 mod, for example, Z2. Okay, some kind of orbifolds. So we know how it works the CFT on a torus. We know now how to do orbifolds. And this kind of orbifold is a particular limit of this K3 surface. So it's inside this moduli space. Okay. But these are very special points. So this is kind of a single, from geometrical point of view, it's a singular limit of a K3 surface, but it's not singular from the point of view of string theory. Essentially because the B field has some non-trivial flux around the singular points there, and then this string theory is very happy in this space. Okay, so this is a nice K3 model, but it's a submanifold. There are other models that we know very well. For example, models that are called Gepner models. Okay, so Gepner models are rational conformal field theories that can be interpreted in some cases as K3 models. So this we also know very well. So these are like zero measure sublots in this moduli space. Everywhere else, we know very, very, very little, okay? So just to give you an idea of how this moduli space looks like, I will not use it, but just to, so this you can describe as a kind of symmetric space, like a coset. This is the real orthogonal group 4,20, and you divide by S of 4 times S of 20, which is a compact subgroup. And then you also have to divide by some discrete group, which you can write like this. Okay, so this is some kind of double coset like that. And if you make calculation, this is 80-dimensional, and this is some discrete identification, so it has some kind of orbifold kind of things. So if you ever seen compactification of heterotic strings, you will notice that this looks very much like an Arine modular space, and that's not an accident because that's related to the fact that type 2A on K3 is dual to heterotic strings on T4, okay? And so this is a non-perturbative duality. So the worldsheet theory, perturbative worldsheet theory here is completely different from the perturbative worldsheet theory here, okay? But the moduli spaces of the two theories must match because there's a duality. So the moduli space is this thing, and then you have the dilaton, essentially, okay? So So the dilaton, in this case, you're in one side of your dilaton modular space where this is weakly coupled and this is strongly coupled, and then this is the other side. Okay, but then the rest is the same. So this is what I want to say about the modular space. That's it. Okay, so what do we know in general? So one thing that we know, and it's true for all these models, is that there is some, well, you can ask about the chiral algebra. Okay, that's what we learned to do for CFTs, right? So the chiral algebra, what we know is that there is a holomorphic and anti-holomorphic copies of the n equals 4 super Virasoro at central charge 6. So it's both, it's one copy holomorphic and one anti-holomorphic copy. So what is this chiral algebra? You probably know, but so there is a stress tensor, and then there must be, oh, let me start from n equals 2. Okay, yesterday we saw n equals 1. Okay, n equals 1 has just a stress tensor and one holomorphic supercurrent. Okay, this is n equals 1. Okay, with conformal weight 3/2. If you go n equals 2, then you probably want to have 2 supercurrents. Okay, but you can't just stop here if you are super conformal. You have to add also U1. A U1 current equals 2. Okay, and this comes because essentially the commutator relation, these guys cannot close just here. You need to have something else. And so the U1 symmetry here is the R symmetry, essentially. Okay, and these two guys are charged. This. And then if you want n equals 4, so yeah, I don't know. Maybe we write just one commutation relation. So this has, so for example, if you have the G plus R and G minus S modes, then you have commutation relations that look like 2L plus S plus R minus S, and then here you need to have your U1 current, and then you have some central term C equal 3 R squared minus 1/4 delta R plus S comma 0. Okay, this is for one of the various commutation and decommutations of relations of the algebra. So this guy must appear here in the n equals 2. N equals 4, you want to have 2 more guys. So you call them G prime plus minus, okay? But then you can't stop with only one current. You need 3 currents that make an SU2, okay? So have G plus minus D, and then you have a G3. So this is SU2, a fine algebra, at level C over 6. This is in general what happens, okay? And so these two guys have the same relation here with the J3. Now, these two guys have exactly the same relation with the same J3. And what the other J plus and J minus do is they mix these 4 guys, not in the way you would think. So they don't mix this with this plus with this minus, but they mix this minus. This is a doublet of SU2, and this plus and this minus is another doublet of SU2. Okay, so they mix these 4 guys in this way. Okay, but the G plus G minus, the Virasoro appears in these guys. Okay, so that's more or less the way the algebra is done. Okay, great. So we have holomorphic, anti-holomorphic, and then you want to build your space of states taking representations of these algebras. So what are the representations now at central charge 6? So central charge 6, that means that you have SU2 level 1, which is one of the things that I gave example yesterday. So representations of n equals 4, c equals 6. So you have various kind of representations. So the representations in general, you can label them by the conformal weight of the ground states. So I'm talking about the unitary representation, only unitary representation. So you have the ground conformal weight of the ground state, and then you can put an L that is the index of the SU2. Okay. Now, since it is level 1, this L for the ground states can only be 0 or 1. Okay, you have from 0 to k. Okay. Now, so you have two kinds of representations. So now, okay, first of all, of course, depends if you are on the NS or Ramon sector. So in the NS sector, these guys are half integral moded. In the Ramon sector, they are integral moded. Okay, so you have two versions of the algebra if you want. And you have different representations. So in the NS sector, you have a 0, 0 representation, which is good because you want to have a vacuum. Okay, and then you have a 1/2, 1 representation. Okay. Now these two representations are special. Okay, because they are, as you can call them BPS representation or short representations. So they are representation where some special modes of your current algebras, they just annihilate the ground states. In particular, the G minus a half. The G minus a half modes are important because they are the ones that preserve the vacuum of your CFT, and you want them to see if there is some ground states representation that is good. So they preserve half of this. They're invariant under half of these G minus a half guys, so they are short representations. Okay, so these are two short representations, and then long representations. Well, you can put any age, essentially, and 0. And yeah, maybe you want to have it greater than 0 if it is. Okay, so these are short, and these are infinitely many long representations. Comment, clearly this is not a rational CFT. You have infinitely many representations, a continuum actually. Okay, so bad, you will not be able to have the characters of this guy will not be vector valued modular forms or nice, modular forms under congruent subgroups of a cell to Z. So this is the Ramond, and then you have something similar in Navier-Schwarz. So this is Navier-Schwarz. In Ramond, you have to start from C over 24. Okay, the level of Ramond has to start from C over 24 by unitarity. So in this case, it's 1/4. So you have 1/4 1 and 1/4 0, which are short representations, and then you have H plus 1/4 1, which are all long representations. Okay. So we have to build our space of states taking tensor products of one holomorphic guy and one anti-holomorphic guys, depending on which sector of your theory you're looking at. And one last property is spectral flow invariance. So spectral flow you can actually define already for n equals 2 superconformal algebras. Okay, so n equals 4 is just an extension of n equals 2, if you want. So you add some more currents. So what is spectral flow? So it's a transformation of the modes of your current. So let's do it. Everyone does it in n equals 2, so I do it n equals 2. And then you can, okay. So these are the modes of your n equals 2. And then you transform them. So say it's spectral flow with parameter eta, okay, and acts in this way. So it shifts the mode of supercurrents in a way that depends a bit on the charge. Okay, it's plus or minus eta. Okay, and then it shifts this guy by something like that. So I do it very generally. Then we're interested in C equals 6. Okay, shifts the 0 mode. Shifts only the 0 mode, so this guy per constant. And then it shifts the Virasoro generators. I hope my eta is a bit different from my n, but C equals 6 eta square delta n 0. Okay, eta is not, but that's what people use. Okay, what does it mean, this thing? It means that if you take all the commutation relations of your algebra and you do these replacements, the commutation relations are still valid. Okay, so you replace these things on the left, you replace these things on the right, and the relation is still valid. So it's an automorphism of the algebra. Okay, that's what it is. And so this eta, well, if you want to be extremely formal, you can take any real number, and it works. But maybe you don't want to be so formal because then you have stupid modings. So probably you want to have eta to be half integral. Okay, but I mean, from an algebraic point of view, you can do this thing, but maybe you want theta half integral. And eta half integral is interesting. So because if you take plus minus a half, you go from Never-Schwarz to Ramond, okay, algebras. So you are changing the mode of the supercurrents by a half, so you can move from Never-Schwarz to Ramond. Okay. And this extends to the n equals 4 algebra, and there you have to be a bit careful because also the j plus minus shift the modings, but they shift also always by integers because, I mean, the shift of the modings depends on the charge, okay, under J03. So this will be the 3, okay, in the n equals 4, and then the j plus minus and shift by 2 eta. So in this case, they shift by integers, plus minus 2 eta. So, okay. Anyway, you can understand this, and that's it. Okay, now this is for the algebra. When you have this is somehow an outer automorphism of the algebra. That means that a single representation doesn't stay itself under this thing. It changes in a different representation, usually. Okay, and this you can see because you change from, if you take eta half integral, you change from Never-Schwarz to Ramond. So it has to exchange a Never-Schwarz representation with the Ramond representation. And how does it exchange? Well, that's the reason why I ordered them in this way. It exchanges them in this way. Okay, so exchanges short with short, long with long in this way. So this is spectral flow, eta equal plus minus half. Now, this is just a symmetry only of the chiral algebra. If you have a CFT, the CFT you have to put representations of this thing, and in principle, you can put the representation you want as long as the partition function is modular invariant, you're happy. So in principle, you don't need to put, if you put some representation H in the NS sector, you don't have to put a corresponding representation in the Ramond sector. You can do a bit whatever you want, maybe, okay? But actually, what happens is that K3 sigma models are symmetric under spectral flow. So the representations in K3 sigma models are, so the spectrum is invariant under half integral spectral flow. So once you have a certain representation in the NS sector, then you have a corresponding representation in the Ramond sector, and then you go back to itself. So let me say that when you do integral, when you do the whole loop, so you go, for example, you take plus a half, you go here, and then you can take again plus a half, and you actually go back to this, but you don't go back to the same states. Okay, you go back to different states. Okay, and the different states are related to this plus minus with minus 1, plus 1. So it's a strange rearrangement of the representation. If you do twice plus a half, you go back in a strange way. That's why it's called spectral flow. Okay, so that's a bit of a strange thing, but that's how it works. So, yeah, exactly, yeah. So, very good. So what this tells us quite some things, because for example, your CFT will have a single vacuum. Okay, a single vacuum means that you have only one representation, which is 0, 0, tensor 0, 0 in the NS sector. Okay, and then you can do the spectral flow to the Ramond sector, and this tells you that you have only one representation in the Ramond sector, that is 1/4 1, 1/4 1. So this must have multiplicity 1. Okay. The other guys, you don't know much. That's more or less the only uniqueness of the vacuum tells you something about the Ramond. Okay, these guys. So let me say also that there are only two conformal field theories that have n equals 4, 4, so both holomorphic, anti-holomorphic. Okay. N equals 4, 4 superpower algebra, and they are spectral flow invariant. Well, I used SF, so invariant. And these are nonlinear sigma models, so K3 sigma models and T4 sigma models. Conjecturally, and okay, unitary and compact and blah blah. Okay, and discrete. Okay, unique vacuum. Okay, some basic requirements, but then the basic ones are n equals 4 and spectral flow invariance. These are the only two guys that we know. Probably, conjecturally, the only two guys that exist with these properties. Okay, but we cannot prove this. Okay. Another thing. So now you can start to say, well, what kind of representation do we have? At least so you can have like short representation, or short long, or long short, or long long, okay? Because you have to put tensor products. So let me also say another thing. When you have, let's say, 0, 0 on the right, and you have something like a half 1, so this is an S sector on the left. So this is so the ground, if you look at the ground state here, this is a holomorphic field, okay? What kind of holomorphic field? Well, the ground state is a fermion, is a something conformal weight a half, and holomorphic conformal weight a half guys are very, very much constrained. They are free fermions. You cannot get anything else. They are free fermions. Actually, it's not only one, because it is a doublet of SU2, so there are at least 2 free fermions. Actually, there are at least 4 real free fermions. That's what happens by CPT things. So if you have one guy like this, then you have 4 real free fermions in your theory, and you have the supersymmetric descendants of these 4 free fermions, which are 4 U1 currents. Okay? What happens is that you have one representation like this. It's a T4 model. So as one can prove it. There's a little more to work, because you can prove it that if you have one guy like this, necessarily you always have another guy like this. And then you have 4 free fermions and 4 free currents on the left, 4 free fermions, 4 free currents on the right. Somehow they saturate the central charge, C equals 6. There cannot be anything else that commutes with them, okay? And these are, so everything in your CFT you can arrange as in terms of U1 to the 4 times U1 to the 4 representations. It's a torus model, okay, always. That means that K3 model cannot have these guys, okay, because it's not a torus model. Okay, these guys are not there. Right. So the short in the NS sector are the vacuum, which has multiplicity 1, and this guy, okay, that has some multiplicity, and that a priori we don't know, okay? So these are the only short in the NS, and there we know the same number must be the short in the Ramon sector, because there is spectral flow invariance. So they have one of these guys, and n of these guys. This is 1, this is n. Let me just stress that this representation, the ground states, is a doublet of SU2. And here the ground states, so the guys that really have conformal weight 1/4 is a doublet, and the guys here is a doublet. So in the end, these guys, you have 4 ground states inside this representation. It's the doublet tensor doublet of SU2, of the 2 SU2s. These guys have a singlet and a singlet, so this is a single one. So if you just look at the ground states, so conformal weight 1/4, this one representation gives you 4 states, and that's it as a representation. And then for each of these guys, you have one more. So you have n of them. So these are the 1/4, Ramon, which are the ground states. So this you know. Okay. Okay, this almost exhausts what we know about these models. So these are not rational. Question, are we sure that the chiral algebra is just n equals 4 and not something larger? So we know that in some special points of the modular space, that this gets extended because we have examples of that. About the generic point in the modular space, we don't know. We don't even know if the generic model has only this chiral algebra. It could be always extended. You don't know. Okay. So you don't know the chiral algebra in general. You don't know the representations more or less apart from this thing that I told you. Okay. So you don't know the spectrum, and clearly you cannot compute correlation functions. Okay. Still, we know a lot more about these models, even at generic points. Okay, and I will tell you this. So what you do is you try to do the partition function, right? So that's what we are instructed to do. And you try to use modularity. Now, partition function, if you want a cell to Z invariance, right, you have to put periodic boundary conditions on your fermions. So you want to look at something like that. So you want to look at the Ramon sector of your theory to have periodic in the space direction, and then you want to do something like this, and then you want to insert this guy to have periodicity in the Euclidean time direction. And this must be a cell to Z invariant. Good? Okay, what happens is that this is indeed a cell to Z invariant, not only a cell to Z invariant, it is a constant. Okay, it's just a number. It's not a function of tau bar. So it's nice, but it's not extremely informative. So why is it a number? Well, this is a supersymmetric index. Okay, this is an index in a supersymmetric theory. So you count bosons and fermions with different sign, and supersymmetry matches bosons with fermions, so you have a lot of cancellations. Okay. If you want to do the things more carefully than just these words, you can say that in the Ramon sector, your supercurrents have 0 modes. Okay, so this is different from the NSNS. Okay, in the NSNS you don't have 0 modes, and then when you try to act with any supercurrent, you change the weight so you don't have the cancellations. But then here you have the 0 modes. Okay, and then if you look at the anti-commutation relation of the 0 modes, you get that's half of this is L0 minus C over 24, so 1/4. Okay. And then essentially, this tells you that these guys cannot have a kernel, okay, if this is different from 0. Okay. It cannot have a kernel means that they just map the space of fermions to the space of bosons, and then it's invertible. Okay. Just it's an isomorphism between the space of fermions, space of bosons, and then in this trace they just cancel out. So the only case where you don't have to have cancellations is when this guy is 0, because then these supercharges can have a kernel, and then the number of fermions and bosons can be different. So that's a usual story with supersymmetric indices, just repeated in this case. So that means that the only contributions that don't cancel out here are the ones where this is 0. Okay, and the same from the anti-holomorphic side. You have only contribution from this where this is 0. So this is a constant. So, okay, good, but you don't know much. Oh, one thing that you know, so you can do the same thing on the torus model. On the torus model, you have not only the supercharge, but you have also the free fermion. Okay, and the free fermion pairs up everything, even at the ground states. Okay, because you have a Clifford algebra of free fermions, and the Clifford algebra just pairs up. So for the torus model, this thing is 0. It's a constant that it is 0. For K3 model, it doesn't have to, and it will not be. Actually, it cannot be 0. Okay, this I also tell you. Why? Because if you look at the 1/4 guys, what you get 4 of them from here. And what happens is that the ground states, so these ground states have a fermion number -1, but also these guys have fermion number -1. So since So the fermion number depends a bit on the SU2 representation you're in. Okay. So what happens is that altogether they have fermion number plus 1. So they are 4 bosons, but also these guys are 4 bosons, are bosons. So you have 4 plus n guys all entering with the plus sign. The minus sign will be the guys with the cross. Okay, but these are forbidden because these only appear in torus models. Okay, so you know that you have 4 plus n here, so that this Witten index will not be 0 for K3 model. So if you want to distinguish a T4 model from a K3 model, you compute this. If it is 0, it's a T4 model. If not, it's a K3 model. Okay. Up to now, it can be any number, but it cannot be any number. And here we go to Jacobi forms. Okay, we want to know more. Okay, this is not enough, right? We have too many. It's nice to have a cancellation, but not too many, because otherwise we can't say much. So, right. Right, exactly. But yes, you can do that, and people did that, and that's what. So I didn't want to do that, but you can do it on T4 mod Z2. You compute it, and you get 24. So random number, which is correct. Okay, so you get 24 if you compute on one K3 model, and then you know that if you deform the model, okay, this should change continuously with the moduli, but it also has to be an integer. So integers that change continuously tend to be constant, okay? So it will be 24 all over the moduli space, okay? So this we know. So we know that n is 20 if you do this calculation. So this is how people knew that you have 20 of these guys, okay? Which means that on the Ramon side, on the NSNS side, you have 20 of these guys, okay? As it says, 20 of these guys, these are doublets of SU2, okay? So actually, you have 80 of these guys of weight a half. Roughly speaking, these 80 guys are the deformations, the 80 directions where you can deform your K3 model, okay? So the true thought is that some supersymmetric descendant here inside, you have 80-dimensional space, supersymmetric descendant inside that corresponds to deformations of your model. And you should think as being like the tangent space in the moduli space of your model. So it's 80-dimensional, and you can check from here that you get the 80-dimensional space, for example. Okay, so these are exactly marginal operators in your theory. Okay, good. So what can we do to get something better? You can look at the elliptic genus. So, okay, now some people would call this elliptic genus. Okay, actually, if you have 0, n, so this you can do whenever you got supersymmetric things, you get cancellations. Okay, if you have a 0, n superconformal field, then you get something nice because you have cancellation only on the anti-holomorphic side. And so this means that this gets contribution only when L0 bar minus C bar is 0, but then you can get contribution from non-zero things, and then you get holomorphic stuff. So that's nice in a 0, n superconformal field theories, then you get non-trivial holomorphic functions of tau, and these must be modular, so this can tell you a lot about the theory. But here But this is not the case here because it's an comma n and you have too many cancellations. So what do you do? Well, let's call it like this. Instead of looking at the function of a single variable tau, you try to be a bit Jacobic. You add another variable z. Okay. So what you do is the following thing. You take the same trace. Okay. Now, this would have cancellations, but what you can do is you can try to count states giving different weight to your SU2 charge, at least the holomorphic SU2 charge. So you can count, okay, different things with the SU2 charge. So if you keep track of the SU2 charge, that means that, let's say that I call y equal to pi I z. Okay, this is similar to Q. So you can do things y to the J03, for example. Okay, you insert something like this. So this is a zero mode, commutes with L0, and it's fine. It's only I put only the holomorphic side, okay? So what I'm doing is I'm counting things, keeping track of also of the SU2 charge, okay? And now this helps because I don't have cancellations which are due to the left-moving supersymmetry charge, because this still pairs up bosons and fermions, okay, the G0 plus and G0 minus, but it also changes the charge, okay, because G0 plus and G0 minus are charged. So this means that they enter with different sign, but also with different powers of y, and they don't cancel anymore, okay? So this works with the holomorphic supercharges. With the anti-holomorphic supercharges, on the other hand, they just commute. We don't see this guy. So here you have the cancellation, okay? So the bottom line is that the only states that don't cancel out are the ones where this is zero, because the other ones are paired up by your anti-holomorphic supercharges, and then you get zero. Okay. So the only states that contribute are the ones with L0 bar minus C bar over 24 equals 0, and then you get something holomorphic in tau, but you don't get the constellations for the other guys. So you get a nice Q series, right? Now, little problem. Is this modular? We inserted something inside, and this something might transform. Actually, it will transform under conformal transformations, because this is a current exponentiated. It has some kind of transformations where you do the conformal transformations. Yep? Yeah. Not? Yeah. It's you can think about it as a fugacity. One thing is that this Z, we like to take it complex, while maybe you would prefer sometimes to take it, if you just have a U1 charge, usually you would take it to real and just count like that. This is complex, so yeah. But so why would we like to have a complex? So what are the properties of this guy? So the way I normalize J03, the charges are integral, so that's just my normalization, but it's useful, which means that this is periodic. Z goes to Z plus 1. So that's nice, and we say, okay, we're kind of on a torus, okay? It's a periodic on one cycle. Maybe we can hope that it is periodic also on the other cycle, and we would have a doubly periodic function in Z, okay? And from the way it is constructed, we don't expect any singularities in Z, so it should be a holomorphic doubly periodic function in Z. That's a bit difficult to have a holomorphic doubly periodic function that is not constant without poles. So, okay, that was hoping a bit too much. But what happens is that if you use your full spectral flow invariance, okay, by a full plus or minus 1, what this gets, so this thing, what happens is that L0 gets mapped to L0 plus J03 plus 1 as central charge 6, so that's what happens, and J03 gets mapped to J03 plus 2, okay? So this function must be invariant under spectral flow. Yep? No, you can pick any half integer. Not in 1/2 plus Z. You can take 1/2, 1, 3/2, 2, 5/2. You can take exactly. That's one possibility. You can take integer or half. Yeah, sorry, it's not 1/2 plus an integer, but either integer or half integer. That's the right word. Yeah, I want to stay in the RR. I want to stay in the RR sector, so I do the full loop. And if you do this thing, what you get is the following. Okay, so the 0 gets shifted by a J03, so you get a Q to the J03 that appears. Okay, and then you get this plus 1 is an additional q. Okay, so what you do, if you do this transformation, you get an additional q. You can just bring it out of the function. You get an additional y squared. And then the fact that you have a q to the j03, you can trade by saying instead of putting z, you have a z plus tau. This gives you a q to the j03. So. Okay, this is what this transformation does to the litigenes. And if the spectrum is invariant, this must be equal to the standard litigene. So it's not quite periodic in Z. I keep changing order here, but it's like that. Okay, it's not quite periodic. It has these two guys, but these two guys are actually, if you rewrite in e to the 2 pi I, blah 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 blah, these are very very similar to the transformation of the theta functions. Okay, there are factors of 2 that are a bit different. Theta function would have some different stuff. So these guys transform as theta functions, and so they must have the same kind of properties as theta functions, and this is what happens. And now, in the minus, no. So what are these guys? These are particular kind of Jacobi forms. Okay, so these are Jacobi forms as the ones that, similar to the ones that Oliver introduced, but they are Jacobi forms with non-zero index. And the index is what you see in some transformation, in this transformation here. So, what is a Jacobi form? A Jacobi form is something like that in general. So a Jacobi form of weight k, and then I put also an index. It's something that has some, so it's a function from upper half plane times C, so tau and Z into C. It's holomorphic here inside, so I take it holomorphic, and then what happens at the cusps, there are many possibilities, so I will see later. But then it has the periodicity conditions. So if you have Z plus, so let's say lambda tau plus mu, lambda and tau, lambda and mu are integers. Okay. So if you do periodic thing, you have the same guy, but with some factor here, which is e to the minus 2 pi I m. This is the index that appears here, and then you have lambda squared tau plus 2 lambda z. Okay. And modular transformations. And the modular transformations are kind of, so you want to transform also z, okay, in the usual way, okay. So you have c tau plus d to the k, as usual for a weight k, but then this, if you just add this is not compatible with this quasi-periodicity. Okay, you can check, this is completely incompatible. There's essentially only one way to get compatible, which is the one, roughly speaking, the one of the theta functions, which means that you have a factor which is e to the 2 pi I m c z squared over c tau plus d. So this is all exponentiated, and then you have pi of tau c. Okay. So these are the elliptic and modular properties of Jacobi forms. Okay. And then you can have, and then you can actually decide to have, I don't know, meromorphic Jacobi forms. If you allow poles, you can have Jacobi forms. So here A, B, C, D can be in a cell to Z, but then you can also take Jacobi forms for subgroups of a cell to Z. Here you might have difficulties to take Jacobi forms for groups that are outside the cell to Z because it messes up with these lattice conditions here. So let's say inside a cell to Z, okay? And so you have all the possibilities. It can be holomorphic at the cusps or not holomorphic at the cusps. Okay, you can have maybe some poles at the cusps. Now they are periodic. In Z goes to Z plus 1, and if it is for cell to Z, it also in tau goes to tau plus 1. It's periodic. Okay, so you can write an expansion, a Fourier expansion in Q and Y. Okay, so you have a Fourier expansion like this. C, some Fourier coefficients, Q to the N and Y to the L. Okay. But actually, so in principle, this could be independent, but actually, the quasi-periodicity in the tau direction tells you that these are not just a random function and L. Okay, these functions. So this is, let me write it. This is small c. Okay, these must be actually functions only of the combination 4mn minus L square. Okay, except. Okay, so this is the some invariant combination. This is why this comes from the quasi-periodicity in the tau direction, where this m is the index. Because this m is fixed and n and L you can vary. Actually, there's also dependence, a little bit of dependence explicit on L, in the sense that this depends on L, but only mod twice the index. Okay, so this comes from the quasi-periodicity conditions. Now, just to see what happens at the cusps, so the easiest thing that you can think is, okay, I want only non-negative powers of Q, so that when Q goes to 0, I have nothing. So these actually are called, a bit confusingly, weak Jacobi forms, even though you would expect a pole, but so weak Jacobi forms means that in this sum, n must be greater or equal than 0, or Cn is different from 0. They're not called holomorphic. Holomorphic Jacobi forms, I put a slightly stronger condition. That is that these guys are, for any thing that you can have here, and anything that you can have here is 0. Let me say minus d. Okay, this is a discriminant, like L square minus 4mn is a discriminant of a quadratic equation. Okay, so this is minus the discriminant. This is weird, but yeah, people do like that. So if this is negative, you want this to be 0. This is what people call holomorphic Jacobi forms. Okay. So what you get, so theta functions come very close to being Jacobi forms. They're essentially Jacobi forms of weight a half and index a half. Okay, so if you look at the periodicity transformations, these are the periodicity transformation of theta functions, Jacobi theta function with m equal half, but with some weird signs, okay, popping out here and there, okay, which is, yeah. But if you take some powers of theta functions, then the signs go away, okay, even powers of theta functions, and then you're happy with the Jacobi functions. Another nice example is, since I don't know if you noticed, but I like lattices. So if you take a lattice, L, okay, we attach to a lattice L a theta series. Okay, I say even lattice L. Okay, and the theta series was something like, so I leave some space here, or quite some space, sum over lambda in L Q to the lambda square over 2. Now you can modify a little bit this guy. You choose a vector in your lattice, choose one, call it V, okay? And then you add a second variable and you put Y to the V scalar product with your lambda. Okay. And this is, so if this is a d-dimensional lattice, this is a Jacobi form of weight d over 2 and index the norm, the square norm of your vector over 2. Okay, this is, if this is even, so this is a vector in your lattice. If this is even, this is integral index. Actually, under some, in general, under some subgroup of a cell to Z. Okay, because if you have a generic even lattice, if it is self-dual, then it is under the full cell to Z. Okay. You can do even more fancy things if you want. Okay, if you choose someone in the dual space, you can do a translate of your lattice, and then just do the sum over the translate. You usually ruin a bit the modular properties, but okay. But this is still integer, okay, because now lambda is a lattice vector with something in the dual, so the scalar product with this is still integral, so you have still periodicity in C, and you can prove that you have also the other periodicity. And actually, when you do a cell to Z transformations, these guys tend to transform into one each other for various choices of gamma. Okay, that's what happens. Okay. Now, this property here tells you also that you can do, so just to make you notice, this property here is the elliptic property, if you do a bit the comparison, for an index 1, Jacobi form. Okay, so this qy square here, if you take lambda equal 1, and so if you take this to the other side, okay, and you take lambda equal 1 and m equal 1, you get q to the minus and y to the minus 2. Okay, so that's exactly the right transformation with index 1. So this looks like a Jacobi form of index 1, and I think it will be, you expect a weak Jacobi form, actually, because the powers of q here are covered q to the L0 minus 1/4, and you are always, the lowest power is q to the 0 in your elliptic genus. So you expect that to start from 0. So you expect a weak Jacobi form. Of index 1. And probably you don't want conformal, you don't want modular weight, okay? And especially because when you put z equals 0, you get a constant. So you put z equals 0, that means you take away your y to the j0, you go back to the elliptic index, so you have a constant. You have 24. So that is modular invariant. So you probably want weight 0 here, because otherwise it wouldn't be consistent with this thing. So this must have weight 0. Okay. Okay. Two more things. So one is the following. Are we? Very much? Okay, I should have stopped at the past, something like that. Ah, I was going for noon. I thought, okay, great. I'm going to noon. No? Okay, sorry. Yes. Okay, so sorry. I got confused with time. Sorry. Sorry? Oh, this is just to say that these guys are not, random function of n and l, but they just depend on n and l through this combination, okay, and only on l mod 2m. So this is the only thing. So every time you have n and l with the same combination, then it must be the same number. That's the thing. Okay, yeah. And we will use this to rewrite Jacobi forms in a nicer way, actually, too. So what So at the end of the day, what this tells you is that you can rearrange things in such a way that you can rewrite the Jacobi forms in terms of theta functions and modular forms and things that depend only on tau. So you can throw all your z dependence inside some theta functions because this rearrangement tells you that all the z dependencies appear in this way, and then you just have to combine these theta functions with some function only of tau, which will be modular some way. So you can, in this way, even if you have two variables, essentially the theta functions, you know how they work, and then you just work with the modular forms that combine them. So you can map Jacobi forms to vector valued modular forms. That will be nice. Yeah, sometimes, yeah, depends on people's taste. I mean, yeah, yeah, I do like Jacobi forms. There's a Jacobi forms tomorrow. Jacobi forms have a ring structure similar to modular forms. So you can do the same thing that we do with the G4 and G6. There are generators for Jacobi forms, and that's great because you know a basis. When you know when you know the weight and the index, you can find your Jacobi form like that. But sometimes you would like to have a theta decomposition. I mean, because that tells you, encodes all the elliptic properties in one place, and then you just look at the modular things. You get rid of the variable. So some things are easier there. Yeah. Yeah. Yeah, this I think depends. It probably depends on maybe the theta decomposition. I would guess. Because actually no, it does depend on the theta. So when you decompose into modular forms and thetas, then the modular form. What happens is that the Fourier coefficients of the modular forms are these coefficients here. So if you want the corresponding modular forms to be holomorphic, then you get this. Yes. Yes, that is not obvious. Yes, because you can, uh, yeah, because you can. I mean, if you have something too negative, you can find an end that goes under zero. No, because this must be, this must be the same every time you have an and L. This gives you this, and then you can find a negative L that gives you the thing if you allow for this. That's more or less the thing. Now it maybe depends on the index. I mean, there's a bit of mess there, but more or less it should be